Hello everyone, we are the Baja Racecar analysis team. First, we ran a static analysis with the chassis treated as beam elements. A side impact at varying speeds was simulated. The chassis was either fixed on the opposite side of the impact or at the wheels. The individual forces range from 6,500 to 26,000 pounds at each joint, depending on the speed. With the side fixture, the stress is exclusively distributed across 4 members. We can see that the stress is linear at varying speeds. The wheel fixture stress plot shows a very high concentration of stress in a small area, with stresses greatly exceeding the yield stress. As the members experience high stress in longitudinal direction, we also ran a buckling analysis. As expected, the side fixture performed worst under these conditions. The joint was cut out of the chassis and analyzed as a side impact. The simulation used solid elements instead of beam. Both linear and nonlinear static analyses were performed under several different types of boundary conditions. Front impact static and buckling analysis was also run with the fixtures either on the back or at the wheels. Stresses were concentrated in small areas. To improve the chassis performance, 12 members were added, which we can see here in blue. While the chassis still fails under some circumstances, we can see significant improvement across the board. A modal analysis was also run on the chassis, either fixed at the wheels or with no fixture at all. There are 6 rigid body modes, and the first elastic mode is about 48 Hz, the second mode number on the wheel fixture. For our closed form solution, we fixed the rear of the vehicle while loading the front with a downward force of 26,000 pounds. By simulating the vehicle as 4 simply supported cantilever beams, we were able to calculate the bending stress, which closely matched a SOLIDWORKS solution. However, the calculated deformation varied from the SOLIDWORKS value, possibly due to an oversimplification of the model. For our analysis on the engine, we ran a thermal study on the cooling fins using 2 different convection coefficients and 2 different bulk ambient temperatures to simulate desert heat. After noting high temperature loads, we increased the surface area of the cooling fins, resulting in decreased min and max temperature values. Continuing our analysis on the engine, a static study was run on the piston assembly at 3 different temperatures. The load was applied to the inner face of the cast iron piston, while a hinge fixture was applied to the connecting rod elements. As a linear analysis, the temperature load increased stress and displacement appropriately. For the frequency study of the engine, a centrifugal force of 3,000 RPM was used. For the first analysis, the bottom of the engine was fixed. For the second, we added a second fixture to the crankshaft rod. An SN curve is done on the wrist pin with an estimated engine life cycle of 10 to 15,000 miles. The engine mount was designed using an X-mount configuration. After running a static and frequency analysis on the part, we created a design iteration for it using a completely flat plate instead of the X configuration, which resulted in much lower stress and displacement. The motor mount may not play a significant role in the overall weight of the car, but it is an option to consider when choosing between reliability and performance. Next, we created and analyzed an external body comprised of multiple components. The front end of the body is made of plain carbon steel. Buckling analysis was performed since the component is long and thin. To simulate a 20 mph crash, we added a 104,000 pound load to the front while fixing the interfaces of the mounts. The results show it doesn't buckle. The front end was then subjected to a static analysis with a reduced load of 26,000 pounds. The results show that the part yields. To help with this problem, triangular supports were added to reduce the max stress. However, this is still far above the yield strength of the material. In order for the part to not yield, we would have to drastically increase weight. As the Baja race car will be moving across rough terrain, we fixed the windshield and side panels to the mounts and ran a study to determine its natural frequency. Thank you for watching our FEA analysis of the Baja race car.